Welcome to this channel. Before we begin, a quick announcement. I'm Ollie, your democratically elected new voice for Michelle. The votes are in, the outcome is clear. Thank you for your trust. I will try not to glitch under pressure. In previous videos, whenever I wanted to build a steel or aluminum enclosure, I kept tripping over the same obstacle. Without a spot welder, making a decent box is an awful lot of work. So naturally, I decided the sensible solution was to build a spot welder first. Now, I'm definitely not the first person to have that idea. Oh no, not even close. Dozens of more and less creative souls have gone down this path before me. The internet is practically groaning under the weight of DIY spot welders. So why not simply copy one of them? Well, this may sound slightly arrogant, but I find most of them underwhelming. Many are rather chaotic constructions, aesthetically adventurous, and generally too underpowered for anything beyond politely attaching very thin bits of metal to other very thin bits of metal. A popular choice for the heart of such a machine is a transformer. Preferably a powerful one, which usually translates into an expensive one. Quite often, a microwave oven transformer is converted, because in our throwaway society they can be had for next to nothing. I will be using one as well. However, in my case it will not be the true heart of the welder because, well, that revelation is reserved for later in the series. My ambition is to build a beautiful, powerful, well-adjustable, and genuinely capable spot welder. I do not merely want to weld flimsy nickel strips onto rechargeable batteries. I want to do real spot welding, ideally up to 2 sheets of 1.5mm steel. And of course, it should also be compact. In other words, I want everything. Preferably in a small box. In this and the upcoming videos, I will take you along for the ride. We begin in proper hunter-gatherer style, sourcing and dismantling an old microwave, and extracting every remotely useful component from it. A perfectly respectable way to spend an afternoon. Here I open up the transformer by milling away the weld seams with a 2mm carbide end mill. Taking it easy since the clamping setup is anything but rigid. While you watch me dismantle the transformer, I have a moment to share a bit of basic transformer theory. A transformer has at least 2 coils, a primary winding, which in this case is connected to the mains voltage, and a secondary winding. When the primary is connected to alternating current, it generates a magnetic field in the figure 8-shaped laminated core. The secondary winding captures that alternating magnetic field and, in turn, produces an alternating voltage of its own. The magnitude of that secondary voltage depends on the turns ratio. If the primary is connected to 230 volts and happens to have 230 turns, that is effectively 1 volt per turn. If I then make 3 windings on the secondary, it would deliver a meager and very safe 3 volts AC. In ideal, highly simplified theory, the total power on both sides is equal. So if the primary consumes 900 watts, the secondary can also deliver 900 watts. The voltage may change, but the power balance remains the same. And in that power balance lies the key to the welding transformer. Because what happens, as you will see me do later, if I give the secondary coil only 3 windings? That gives us a secondary voltage of 3 volts AC and an available power of 900 watts. Since power equals current times voltage, that means the secondary current becomes 300 amps. So in theory, we end up with exactly what we want, a welding current of 300 amps at 3 volts, delivering 900 watts. Low voltage, very high current. Which is precisely the combination that makes metal stick to other metal instead of blowing fuses or exposing you to life-threatening electric shocks. Of course, reality is less cooperative than theory. This transformer was originally designed for a secondary winding that produces a life-threatening 2000 volts AC. It is therefore somewhat optimistic to expect my modest 3-volt secondary to handle the full theoretical 900 watts with great efficiency. My own estimate is that perhaps 500 watts will actually make it across. That changes the arithmetic. 500 watts divided by 3 volts gives about 166 amps. After accounting for additional losses, I arrive, by the highly scientific wet finger method, at roughly 150 amps at 3 volts AC. As easy as it was to remove that laminated bar, getting the windings out of the transformer turns out to be a very different story. They are wedged in unbelievably tight, and it takes well over a ton of pressing force to shift them. This is where I am very happy with the small hydraulic press I built a year ago. It handles this job without the slightest complaint. After separating the windings, I discover there is actually a third coil with 3.5 turns. Excellent. That will serve nicely for an initial test. The original high-voltage secondary, on the other hand, can retire gracefully to the scrap bin. As expected, the primary has 230 turns. That also means the coil with 3.5 turns should deliver about 3.5 volts AC. If it does not, then I may have damaged the primary coil while persuading it back into the laminated core. And if the output is significantly below 3.5 volts, it could indicate that a few turns in the primary are shorted together while banging it in. That would be educational, but far from ideal. Excellent. That went surprisingly smoothly. During the hunting and gathering phase, I also stumbled upon an old set of jumper cables in the shed, which I picked up from a bargain bin some 30 years ago. Back in the days when copper was still cheap and reassuringly solid, instead of plated optimism wrapped in plastic. That's a solid 25 square millimeters of copper core. In theory at least, it should have no trouble handling the estimated 150 amps secondary current. Off camera, I made a few threaded rods and 4 clamping bars. Contrary to what some might assume, you do not need to weld the laminated bar back in place for the transformer to work properly. What really matters is that there is no air gap between the bar and the rest of the core. That ensures the transformer operates optimally. So simply clamping the bar firmly to the rest of the transformer is more than enough. The big bonus? I now have a transformer that can be taken apart quickly, a setup that's going to make the upcoming experiments a lot easier. Well then, look at that. Almost exactly 3 volts. And with a healthy current, since I can heat that steel strip fairly quickly. On YouTube you will often hear claims of more than 1000 amps from these transformers. Yes, that is possible, but only as a short-circuit current. The secondary winding, and the transformer itself, will not survive that for long. At 1000 amps the primary usually pulls well over 2 kilowatts, which is rather unhealthy for a transformer rated at 900 watts. Realistically, somewhere between 200 and 300 amps on the secondary side is about the maximum you can extract from these units without inviting unpleasant smoke signals. To test what I have built so far a bit more thoroughly, I cobbled together a hinged setup with 2 welding electrodes from various pieces of old scrap. Engineering at its finest. I am curious to see what happens when I clamp 2 0.5mm thick steel plates between them. I suspect nothing too dramatic. Perhaps a bit of redness, a few sparks, and 2 modestly fused pieces of steel that look more surprised than impressed. And indeed, it holds. There is a weld nugget of about 1.3mm, and I actually have to apply some force to twist the plates apart. However, the weld time is already a full second, which is far longer than I would like. That is probably not a good sign if I want to weld thicker material. Let's do the same little test again, now with 2 plates 1mm thick. After no less than 2 seconds, the weld is still very weak and the material has clearly not melted deeply enough. It does, however, produce a wonderfully dramatic shower of sparks. The kind of shot a YouTuber might be tempted to use as a thumbnail. Purely for scientific reasons, of course. And with this kind of tinkering around a transformer and roughly 150 amps, many a YouTuber would already be celebrating a historic breakthrough. Meanwhile, here in the real world, I am staring at what can only be described as mildly enthusiastic metal sticking. These are, objectively speaking, rather underwhelming spot welds. I want to run a few measurements, but first I will tidy up the already fraying wire ends by soldering them closed so they stay neat and manageable. I pass a current of 10 amps through the cable while measuring the voltage across its ends. The cable is 2 meters 20 long and shows a resistance of just over 2 milliohms, which matches the theoretical value quite well. So yes, this appears to be genuine copper. No creative metallurgy involved. Here I perform what could best be described as a spinal tap on the winding. With the secondary short-circuited, I measure the voltage between one end and the freshly punctured midpoint of the secondary winding. The total voltage turns out to be no less than 2.56 volts. According to Ohm's law, that corresponds to a secondary current of well over 1100 amps. Which sounds heroic, right up until you remember what usually happens next. Because over 1100 amps at 2.56 volts amounts to nearly 3 kilowatts. Definitely not a healthy load for a transformer designed to deliver just 900 watts. And since very high currents can occur during spot welding, at least for the plans I have in mind, I need to watch the temperature of the secondary winding. Theory predicts that the temperature rises by roughly 20 degrees per second of welding, which matches this practical test quite nicely. And that most likely means I'll have to strip off that plastic insulation and switch to a heat-resistant covering. Oh well, so be it. How I intend to get from somewhat warm steel to real spot welding you will see in the next part of this series. Before I go, a word of warning. Feel free to take apart a microwave yourself, but cut off the power cord first and wait a few minutes before you start unscrewing anything. Do not open the magnetron tube, tempting as those nice magnets may be. The white ceramic material inside, especially in older units, can be hazardous. Curiosity is good. Staying alive is better.